Welcome to this Mohnblatt ZK Whiteboard session. I am Nico and I'll be today's host. And with me I have Jim from Irreducible.
Thanks, Nico. It's great to be here. Today we're going to talk about small field SNARKs and why this line of work is important. We're going to start with some motivating factors and talk about the performance efficiency that we can get using small field techniques. Then we're going to go through an example of how to construct a STARK like Plonky 2 that uses the Goldilocks 64-bit field. And finally, we're going to talk about some recent work that investigates how small we can make our fields using binary towers. How does that sound?
Yeah, sounds great.
Let's jump in.
Yeah. So you said motivation first. Why would we want to do small field? What do we even mean by small?
Oh, I'm glad you asked.
Yeah.
This really contrasts with the default way that we had of constructing SNARKs prior to, let's say, the Plonky 2 project, which really popularized this. And before that, we would typically use a finite field that is a 256-bit prime number. This is for a few reasons, but one of them is this appears in secure elliptic curves as the field that we want to work in. And also, we can recall that a lot of SNARKs are based on polynomial identity testing. And when we do a randomized polynomial identity test, the false acceptance probability, which is what we're trying to minimize, is inversely proportional to the size of our field. And so if we use a really large field that's 256 bits, we get a very small and acceptable error probability. Now, the problem with these is the performance of field multiplications is much larger with 256-bit numbers than with smaller numbers. One reason is if we look at the computational complexity, the time it takes to do a field multiplication is super linear in the number of bits, which means if I double my field size, I need to do more than twice the work in order to do this multiplication. And also, computers have native registers for smaller elements, integer elements like 64 and 32-bit numbers, so we want to capture that hardware efficiency. To throw some quick numbers at you, you can do, on my computer, about 60 million 256-bit prime field multiplications per second on a single core, whereas it's 1,200 with the 64-bit Goldilocks field. So that's 20 times more field multiplications you can do with a 64-bit field.
Right. That sounds worth it.
The other thing that we need to talk about is when we're actually building a SNARK, we have some sort of circuit. And typically, we need our circuit to express the computation that we want to prove. And the actual values that appear in our circuit trace or on the wires are much smaller than the actual size of our field elements, usually. In a lot of computations, we'll have very small values, maybe 16 bits or 8 bits or even 1 bit, inside of a field that might be 256 bits. And the rest of the bits in that field element are just zeros.
So I'm using this sort of big storage slot of 256 bits for just 1 bit that I'm going to do stuff with?
Exactly. So this seems very wasteful, right? Both in terms of the time to do the field multiplications, but also the memory usage we need to pay for. And bad memory usage leads to bad cache utilization, which again leads to poor performance. So these are some of the motivating factors for why we're interested in building SNARKs and STARKs over small fields.
Okay. Just to be clear, small means closer to our computer register size, so 64 bits or 32 bits or smaller.
Exactly. Cool. Yeah, let's almost by definition say that it fits within a machine register, which is 32 or 64 bits. One disclaimer, I'm going to talk about the STARK protocol, but I'm going to refer to all STARKs as SNARKs. There's a subtle difference, but I don't think it's worth getting into right now.
Cool. So yeah, should we run through a protocol with a small field and see what it looks like?
Yeah, absolutely. Let's refresh on a very simple STARK that we could talk about, which is a Fibonacci example. So we're going to have our computation trace, and this is going to be the Fibonacci numbers, and we're actually just going to have, for now, a single polynomial
Okay,
call this
so a single column in our
a
trace.
single column in our trace, and we'll call this F. And this will have a number of values. And the constraint that we want is that F at I plus 2 minus F, at I plus 1 plus F at I equals 0 for all indices I in our table. There are some boundary constraints that we're going to hand wave aside for now.
So we're saying Fi plus 2 minus Fi plus 1 and Fi equals 0, right? So
that's right.
Okay, cool.
And we want that to hold for every slot.
Right. And then do we wrap around, or are we going to let's just ignore it for now?
We're going to ignore what happens at the very top and the very bottom for now. There's some way that you could compensate for this. But I believe you've talked about STARKs in a previous session and expressed how we can turn this into a polynomial problem. But roughly the way we're going to prove this is with 3 steps, right? Like first we're going to commit. 2, we're going to do some sort of polynomial division check. I'm going to call this the vanishing argument. What we want to show is that this equation vanishes or is equal to 0 over the whole trace.
I think we've called it the 0 check previously.
Okay, let's call it that then. The third step is the polynomial identity test, which is how we're going to kind of finish the 0 check. And then we need to do our Fry evaluation proof. Fry is the fast read Solomon IOP of proximity. I'm going to maybe refer to it as a polynomial commitment scheme in this lecture or in this whiteboard session. Even though there are some subtleties and it serves various purposes.
I guess it fulfills that role, right?
Exactly.
Cool.
So perhaps what we can do is let's run through how this protocol looks when we try to use a 64-bit field for the entire protocol and see what we might need to fix. When I talk about a 64-bit field, I'm specifically going to refer to Goldilocks. And this is a prime number that is 64 bits, or fits within a 64-bit register. And it has a very special structure that makes it computationally efficient to do in a very small number of cycles on a regular CPU. And it's also compatible with STARK techniques in the sense that it allows for the fast Fourier transform that we need. So let's imagine that we have this whole trace. All of our numbers are integers that are sort of embedded within this Goldilocks field, and we want to commit this. This works with no problems.
Okay.
So what does committing look like? Well, we're going to apply an error correcting code, the Reed-Solomon code, and then we're going to build a Merkle tree, and we can...
So is this, the interpolation and the blow up?
Exactly.
Okay, cool.
Yes. And this works perfectly over this Goldilocks prime field. The next step is
I guess unless we take our Fibonacci sequence into like way too big numbers, which don't fit in here, right?
That's right.
Okay.
Yes.
As long as we're working with like 0, 1, and then etc., we're fine.
Yeah, it would take, I guess, yes, that's right. As long as our Fibonacci number stays within this field, we're pretty happy. The next is the 0 check, and I'm not going to write this out sort of completely, but we'll remember that this is basically a polynomial identity test, where what we want to do is we have, this is our constraint, and we want to say something like the composition, which is this constraint, applied to f over a formal variable x is divisible by the polynomial that is 0 everywhere and of appropriate degree. And we're actually going to check this with the multiplication. So we're going to have the prover provide a quotient q, and this is the zero polynomial. And we want to do this polynomial identity check. And if this is satisfied, then we know that this is 0 over the entire trace.
Is this what people call the vanishing polynomial?
This is the vanishing polynomial, exactly. Now, what we need to do in the zero check step is compute this quotient q. The way we do this is we evaluate the polynomial at an extended or over some domain that is where we're not going to get division by 0 elements. We're going to do all of our point divisions in this other domain, and then we're going to interpolate that polynomial to get our quotient q.
Cool. We being the prover?
We being the prover.
verifier doesn't do any of this, right?
That's right.
Cool.
Good point. The prover is going to do all this work and provide a commitment to the quotient to the verifier.
Cool.
And what I want to observe is that we are also able to do this entire process of computing the quotient q for a single constraint over our Goldilocks prime.
Cool.
Now, when we get into the Frye evaluation, this is where we're going to do our randomized polynomial identity test. So what we want to do is we want to pick the verifier chooses an element z, which is a random element from our field. And we want to check that this relation holds at this specific point z.
That's our zero check.
This is, yes.
I think lecture, maybe the second module. Cool.
Now, the security of this is based on the Schwartz-Zippel lemma. And without writing that out completely, what we know is that there is a error probability, or essentially it guarantees us a false acceptance probability that's inversely proportional to the size of the field. This is where we would start to run into a problem, because the size of our field is only 2 to the 64, and really we want an error probability that's less than, say, 2 to the 128 or something much smaller.
Are those the bits of security that we talk about?
Yes, that is what that is sort of by definition what we need to achieve a 128-bit security target.
Okay, and we're not even close right now.
We're not even close. That's right. We would need a much bigger field, like a 256-bit prime field that we sort of were trying to replace in the first place, in order to get this Schwartz-Zippel test to give us an acceptable security level. So we now need to talk about how we're going to fix this with a technique called error amplification. So we're going to talk about how we're going to use error amplification to use the Goldilocks field, but still get a very small error probability, which is achieving a 128-bit security level.
Okay.
There are a few techniques to do this, but I'm going to talk about using extension fields.
Okay. What are those?
Extension fields you might actually already be aware of from high school algebra, where, do you remember learning about the complex numbers and the imaginary numbers?
Yep.
Great. So the idea was that we had the real number line, and we can think of, in our analogy, the reals kind of being like our Goldilocks number. And what we did was we said, we're going to declare that a complex number has the form a plus bi, where I is the imaginary unit. And this basically turns our number system into a two-dimensional plane, where a is along the real axis and b is along the imaginary axis. And now any of our numbers falls somewhere in this plane. The other thing is we knew that we declared that I squared is 1. Sorry, negative 1.
Yes.
We declared that I squared is negative 1. We can do something analogous with the Goldilocks prime. In fact, what the complex numbers are they're an extension field of the real field.
Right. Okay.
And what this means is in extension, we're going to talk about a degree 2 extension of Goldilocks, meaning we're going to have a two-dimensional plane, and every point in our extension field is a pair of Goldilocks field elements.
Right.
Now, this means that the size of our field gets squared. If we count up how many coordinates there are in a two-dimensional plane where each value is a Goldilocks prime field element, we have a 128-bit field, or a field with close to 2 to the 128 elements.
I see. Or I guess one way to say it is also how many pairs of Goldilocks elements can we have?
Exactly.
Right. Okay.
And if we count those up, we see that it is enough to give us a secure Schwarzschild test.
Right.
I want to mention a couple of properties about extension field multiplication because it doesn't come for free. Okay. So let's remember how we had to multiply complex numbers. If we took two different complex numbers, a plus bi times c plus di, and we want to compute this, there are a few cross terms. We have to distribute this out. So we get ac plus...
Oh, this takes me back.
And at this point, when we multiply, we're going to remember that I squared was -1.
Yeah.
But the thing I want to point out is that to do this multiplication of two elements, we actually had to do 4 different multiplications of our base field elements.
Yes.
So doubling the size of our field and operating on pairs turned into 4 cross terms. Again, this is an example of how when you increase your field size, it's a superlinear growth in the multiplication complexity.
That makes sense.
I want to mention one more property, which is if we want to scale a Goldilocks field by a base field element. So in this case...
Sorry, scale an extension field by your base field? Okay, cool.
I want to point out that if we want to scale an extension field element by a base field element, so instead of multiplying an extension field by an extension field, we multiply a base times an extension field. This requires fewer multiplications. So if we took s times a plus bi, we can simply distribute this to be sa plus
sbi. Okay.
So as much as possible, we would like to operate with multiplications in the base field, and the next best thing is to multiply base field elements by extension field elements. But when necessary, we have a way of multiplying extension field elements by extension field elements.
Cool.
I think at this point, we can return to how we're going to run the STARK protocol using the Goldilocks extension.
Sounds good. So back to STARK.
Let's go back to the STARK. Let's start over. So we have our trace with the column F, and we're going to keep this inside of the Goldilocks field. These are not extension field elements yet.
Okay.
And the first thing we did was commit.
So the reason we can do this is because we're working with just small numbers, right? Things that are less than 64. Cool.
Yeah. We, for this purpose, don't need... We can fit within this field, and also we know that every Goldilocks field element is itself living within the extension field. If you think about the real number line that lives within the plane.
Yeah.
So the first thing we want to do is commit our column F, and I claim that we can do this the same way we did before. We're going to do our fast Fourier transform and our Reed-Solomon encoding and our Merkle tree building all over the Goldilocks prime. And this is great because even though the rest of our protocol might have some changes, we still get the efficiency gain here.
So we still save on, having small numbers in smaller storage locations rather than like 256-bit.
Exactly. Cool. So another important thing here is that when we do our fast Fourier transform, minimizing the memory usage of this is really important for performance because it means it can fit in a smaller cache.
Right. Cool.
The second step was the zero check.
This is where things broke down, right? Or I guess with the sampling.
That's right. So there's actually 2 phases here. There's the quotient computation, And right, this is where we just computed the coefficients of our Q polynomial.
Yeah.
The coefficients are still within the Goldilocks base field when we have this one constraint, which means that the work to do this, which is quite a bit of work and quite a bit of polynomial evaluations, we can still do over our base field.
Cool.
The point where this broke is when we did our random testing. Random. And at this point, we're going to do the same thing, but when we take Z, it's going to be basically a pair of Goldilocks elements. It's going to be an
element of the extension?
An element of the extension.
Amazing. Okay.
And kind of remarkably, we can plug that in to our equations where each of these coefficients are from the Goldilocks field and still do this polynomial identity test and now get a much lower false acceptance probability. So we've amplified the probability of catching an error.
So why is that? Because we went from 1 over size of Goldilocks to 1 over size of extension?
Yes.
Okay.
Our extension field, remember, is roughly, I'm going to call this like GL squared for the tuples of the extension. Yeah. And this is roughly of size 2 to the 128.
Okay. Amazing.
Then we're going to move on to our Fry evaluation proof and run the Fry protocol. And without getting into the details of this here, the Fry protocol will itself involve more sampling of random elements from the Goldilocks extension field. But by a similar argument, we can show that the error that the soundness error that we get during the Fry protocol is inversely proportional roughly to our the size of our extension field. And so the same soundness amplification technique works in this step as well.
Right. But now Fry is going to work over the extension?
Yes.
Okay. So no savings really here.
That's right.
Cool.
At this point, we're not getting savings, but we've saved a bunch of work here in our commitment phase. We've saved work in phase 2A, and phase 2B is quite cheap to do for the prover. And phase C, we didn't really save any work, but actually we're just really happy that we saved work in the commitment and quotient computation phases.
I mean, I remember recent talks from Elie Benson where he was saying these were the real bottlenecks. So
that's right.
Good news.
Yeah, that's absolutely true. The Fry protocol is linear in the size of the extended polynomial, whereas the commitment phase is actually really expensive because it involves both the fast Fourier transform, which is super linear in the size of the polynomial, and also a lot of hashing to build our Merkle trees. So if we can even just save work in the commitment phase, we're really happy.
So now I have another question, which is, by this same logic, if I took something that's 64 bits and to get security I extended it, could I take something smaller and extend it more?
Yes, and there's a lot of projects doing this today. So there's 2 smaller prime fields that are used by other projects. The RISC-0 project began using the baby bear prime field, which...
Do you mind writing them out
yes.
if you know them? Or
so let me come back over here. Yeah. So the baby bear field is a 31-bit prime number, and it has the form 15 times 2 to the 27 plus 1. And we didn't talk too much about the fast Fourier transform, but it's actually really important that we have prime numbers with this structure that is some number times a large power of 2 plus 1 in order to...
Oh, I guess we can factor the 2 to the 32
Yeah,
here and
let's
have
do
it as well.
this.
Right.
Good point. We can see that our Goldilocks prime had this property that we're going to call smoothness that allows us to use the fast Fourier transform techniques.
Okay.
There's another prime field.
So smoothness, just to be clear, is this thing, right? This big 232? Or this big power of 2?
It is this form where you have a number times a big power of 2 plus 1.
Cool.
There's another prime field that is gotten attention for. There's a new line of work called circle STARKs. And this is the Mersenne field. And this number is 2 to the 31 minus 1. Now, what do you notice?
Yeah. I mean, they don't have the nice +1 thing.
It does not have the smoothness property as I just defined it. But due to some really creative research, we can actually do something like the fast Fourier transform for the Mersenne field, even though it doesn't have this particular form. And we're interested in doing this because the computation to compute multiplications in the Mersenne field is actually several clock cycles cheaper than doing it even for Baby Bear.
Wow, okay. I guess because it's just a 1, a bunch of zeros, or maybe... Oh,
yeah,
no, not necessarily, actually. But yeah, never mind. Ignore that. But it looks simpler.
If we were to write it out in binary, it would be like a lot of 1s.
Right.
And
okay,
there's nice digital logic circuits that could process multiplications of those numbers.
That makes sense. Can we go even smaller?
Great question. Actually, I forgot before this, what we can do with the Baby Bear field is we still need a field extension.
Right, yes.
And we cannot do just a degree 2 extension, which is a plane, because if we think about how many fields, let's take a degree 2 extension of Baby Bear. I said this is a 31-bit field.
Yeah.
If we think about all pairs of Baby Bear elements, we still only have less than 2 to the 64 total elements. And so in the case of Baby Bear and Mersenne, we would need to use a quartic extension, which is every element of our extension field is a tuple of 4 Baby Bear or Mersenne elements. And there is a multiplication method that would be defined for this. But using basically everything that we talked about for Goldilocks, the rest of the STARK protocol would go through.
Right. Amazing.
You then asked, can we go even smaller?
Yes.
That's a really interesting question. And there are some challenges. So, we could ask, could we use a 16-bit prime field or an 8-bit prime field? And we run into really 2 problems. I'm going to erase this now.
Yeah, sounds good. I guess smoothness, since you were saying we need this big power of 2.
That is certainly one problem. So and let's remember 2 particular phases of this. So one was Reed-Solomon encoding.
For the commit part.
For the commit part.
Cool.
Which is part of the commitment, as you said. And this is the way we implement this is with fast Fourier transforms. And the second was polynomial division,
Yes.
which was part of our zero check.
Does that also need fast Fourier transforms?
It does. We can reuse the fast Fourier transforms that we did during the Reed-Solomon encoding. But the property that both of these have is that we need to treat our F column and interpolate a high degree polynomial, or depending on relatively, we need to interpolate a polynomial over the values that we had in our F column. So let's say,
Like high, you're saying compared to this, but low compared to the size of the extension field, I'm guessing.
yes.
Okay, cool.
So I think for typical SNARKs, we would be talking about columns that are in the range of 2 to the 20 to 2 to the 24. That's a pretty typical size for the height of a STARK trace. What that means is, recall, we're going to associate with every row in this column a different evaluation point from our field.
Yes, the roots of unity.
Yes, the roots of unity.
Also past modules.
Now, we run into a problem if we're trying to use a 16-bit field, because a 16-bit field not only doesn't even have that many roots of unity, it doesn't even have that many points.
Right, yes.
We couldn't possibly have 2 to the 20 evaluation points in an 8-bit prime field.
Makes sense.
So we could use field extensions, but this is starting to get essentially difficult, and we're not getting the same benefits from basically using the efficiency of small fields when we use that.
I was going to ask, if we start using extensions from the beginning, we're no longer having savings like
exactly
points 1 and 2. Okay.
So I'm going to talk about how to solve these challenges separately. Actually, number 2 is potentially the easiest to solve, and I'm not going to go into too much detail, but recall that this was part of our vanishing argument, or our vanishing or zero check argument. And there's another protocol that we could replace polynomial division with called the sum check protocol.
Right.
I believe you may have talked about this in a past or upcoming session. I'm not going to go into the details, but when we use the sum check protocol for our zero check, we actually don't have this limitation that forces our field size to be very large. We can even run the sum check protocol with small field polynomials, again using extension challenges, but this all works really nicely.
Okay, so that's solved. What about encoding?
Right. Solved with sum check. What about Reed-Solomon encoding? Well, let's talk about quickly what Reed-Solomon encoding is. Reed-Solomon encoding, Reed-Solomon is an error correcting code or an erasure code, and what it effectively means is we're going to treat our F column as a polynomial. We're going to interpolate and evaluate it at many more points. So again, we have this problem that we need lots of evaluation points to even define what it would mean to do a Reed-Solomon encoding.
Like even more than the trace itself.
Even more than the trace itself, we can think about some evaluation points down here where we're going to extend our polynomial to. And so it has taken some more creativity to get around this. My team developed some techniques based on a different type of field called a binary tower. And I want to talk about what a binary tower is and how we can both use binary towers and a new small field polynomial to large field polynomial commitment scheme reduction in some generality.
Amazing.
So, have you heard of a binary field before?
I'm not sure, no.
So, let's start with the smallest field we could possibly cook up, which is F2. And this is literally has 2 elements. It has the elements 0 and 1. We're going to use our field extension technique and create a field with 2 to the 2, or 4 elements. And we can think of these as being pairs of F2 elements.
Right. So 0, 0, 0, 1, 1, 0, 1, 1?
Yes.
Cool.
We can also think of this as a 2-bit string. And we're going to just keep doing this over and over.
Right.
And what you may have learned in high school is that this doesn't work for the real numbers, but it does work for these binary fields, that we can continue to build, planes and field extensions. So we could make a field. This should be 2 to the 4.
So we're taking 2 of these elements to make 1 of these elements.
That's right.
But because this was already 2 of these, this now becomes 4. Okay,
Yes.
I see what's happening.
And
I'm
so
gonna keep
we're
towering, right?
yes. So this is I like to think of it in terms of the number of bits to represent each field. So this is 4 bits.
Yeah, that's a lot less confusing than what I was saying.
This is 8 bits.
Yeah.
And we're going to just keep doing this. And we can go as high as we want.
Okay.
For the purposes of this conversation, we'll continue doing this up to F2 to the 128, which is a 128-bit field. And that is enough to give us the security that we wanted for our Schwartz-Zippel test and the rest of our polynomial or our protocol soundness guarantees.
Amazing. So you talked a bit about the costs of multiplication in these extension fields when we were looking at Goldilocks, saying like it gets more expensive as we extend more. Is this also the case here?
This is the case that our multiplication grows super linearly in the number of bits. However, there's some really remarkable ways of constructing this. In particular, we identified one way of constructing this tower that gives us really good multiplication complexity, matching the asymptotic complexity of regular integer multiplication.
Wow, okay.
And notably what this means is when I wrote out the multiplication algorithm for the complex plane, it looked like it would be a quadratic number of multiplications you needed to do whenever you multiplied extension field elements. Remember that we multiplied 2 complex numbers and had to do 4 subfield multiplications. Actually, we can do multiplications in the binary tower with less than a quadratic number of underlying bit multiplications or bit operations. So, you know, how should you think about these? Well, again, this symbol was inclusion, meaning we kind of have this Russian doll of different fields that live one within another. And whenever in our protocol we're able to use a smaller field, we will do that. And then whenever we require a larger field for either more evaluation points or for more cryptographic soundness, we can move up to a higher tower level.
So after this detour, I guess my question is now, how does this solve that problem?
I want to talk about one more concept, which is what we call packing. And this is this notion that because these live within one another, we can take, you know, we talked about a F2 to the 8 element as being pairs of F2 to the 4 elements.
Yeah.
And so if we have, let's say, where should I write this? I'm going to erase this here. An F2 to the 8 element is 8 bits. This is the same size as 1 byte, right? So let's say we have a bunch of bytes. Say we have 16 of them. I don't know if this is going to be 16 slots, but
let's pretend
16 elements that are F2 to the 8. Each one is a byte, so we have 16 bytes. What I'm saying we can do is we could view this in many different ways. So we could actually view this as a single element of the 128-bit field. Or we can chunk this into 4 bytes at a time and treat this as 4 32-bit field elements. And this is what we call packing. It's the idea that we can take small field elements, group them together, and treat them as big field elements. And this doesn't say come for free. There are you know, technicalities we need to deal with, but this is in general a technique that's available to us in the this setting of extension towers that becomes really useful.
It's like kids in a trench coat trying to get to the cinema.
Exactly.
That's what's happening here. Okay.
So I think now we're ready to talk about how we're going to use packing to fix our problem with the Reed-Solomon encoding and basically not having enough evaluation points when we're operating over F2.
Cool.
So the setting here now is we have a column F. It has 2 to the 20 to 2 to the 24 rows in this column, but each element is a single bit.
Okay.
It's an F2 element. And we wanted some way to commit this polynomial and run something like our STARK protocol, but with the zero check replaced with a sum check reduction.
Yeah.
And we also would like to continue using Reed-Solomon codes because they have really good properties and they lend themselves to the Fry protocol.
Yeah.
But we have this problem that if we were to evaluate our F column at a bunch of more points, we could do this by padding them up to 32-bit field elements. So we could kind of imagine that these all were 32-bit field elements, and we would pad with zeros.
Oh, a bunch of zeros. Okay.
But this looks really inefficient for all the reasons that we didn't want to use a larger field in the first place.
Yes, we're back to like small things going into a bigger field storage slot. Okay.
So instead, what we want to do is find a way to take chunks of bits and pack them.
Trench coat.
Yes. So let's imagine that we're going to take chunks of 128 bits at a time. 128 bits here, 128 bits here, and treat them as a single element of a very large field, of an F2 to the 128 field. This is big enough for us to run Fry over.
Yeah.
Now,
does this have the smoothness property we want? Yes, I guess. It's already...
Yeah, it has a different type of smoothness.
Okay.
And what that means is that there exists a fast Fourier transform type of algorithm that can do efficient Reed-Solomon encoding for these binary fields. It's called the additive NTT. It's slightly different from the regular NTT or FFT that we're used to, but it does have a notion of smoothness.
What does NTT stand for?
That's the number theoretic transform, which is when it's a transformation on finite field vectors.
Okay.
And usually we want to refer to using the fast Fourier transform algorithm, which is famously efficient for doing this transformation on finite field elements.
Okay. So NTT is what we want to do, and FFT is the algorithm we use?
Yes.
Cool.
So back to here, we said that we have a column of bits. We wanted to pack adjacent bits into big field elements.
Yeah.
We wanted to use the Fry protocol running over our big field elements and use this to effectively evaluate the interpolation of our column F somewhere. Now, if we were to just do this, this would not actually equal on its own the... So let's talk about two different polynomials. We have F. We have 2 to the 20 F2 coefficients. And when we pack, we're going to take chunks of 128 bits, or 128 elements. 128 is 2 to the 7.
Yeah.
And we can define this as an entirely different polynomial, kind of calculated in this way, which is basically a memory cast on the bits. And instead, we end up with 2 to the 20 minus 7 F 2 to the 128 coefficients.
Right, because we divided our column of 2 to the 20 into chunks of 2 to the 7.
Exactly.
And so the division gives this. Okay.
So these are, what I am saying is that these are actually two separate polynomials. They don't even have the same number of variables, but using a sum check based reduction and a technique that my team developed that we call ring switching, what this lets us do is, if I want the evaluation of F, I'm going to have the prover and verifier engage in a sum check protocol that we call a ring switching sum check. And this is a reduction to a claim about f hat at a particular point. What that means is I'm then going to get a claim about f hat at a point.
Right.
And what it means for this to be a reduction is that if this claim is true, that f hat evaluates to the claimed value at the claimed point, then I should be fully convinced that f evaluated in the way that I wanted originally.
Right.
And what's really cool here is that we were able to do this sort of packing trick on f. We were able to run our Reed-Solomon code over that because f to the 128 is smooth and has enough evaluation points. We were able to run the Fry protocol here, but we were able to do a sum check reduction so that we sidestepped all the issues that we had with using not just small fields, but what I call tiny fields, fields that are way less than the size of a machine register. And so that explains how we're able to use binary towers to shrink the size of our fields.
So just to make sure I understood this part correctly, you're actually only going to commit to f hat.
That's right.
And then to get evaluations of f, I'm going to get evaluations of f hat from my commitment. And then there's this little protocol that translates from f hat to f.
Yes.
Is that correct? Okay, cool. Amazing. Is that like an expensive protocol? Is that a cheap protocol?
It's a fairly cheap protocol. It's roughly the same cost of doing the Fry protocol that we needed to run on f hat anyway. So we can think of it as being a small constant multiple, maybe twice as much work as we had to do. But we're saving a lot here because instead of running f hat for 2 to the 20 coefficients, we're running it for 2 to the 20 minus 7, 2 to the 13 coefficients.
So a factor of 2 here, but there's like 7 factors of 2 removed there.
That's right.
Amazing. Is this what people call Binius, this sort of construction here?
Yes. Binius refers to a project that implements all of these techniques that my team is developing, and it has kind of come to refer to these techniques of using binary towers to construct SNARKs generally.
Amazing. So, correct me if I'm wrong, but today what we saw is we want to use small fields for performance. The problem with that was soundness, that we got this 1/size of field thing. So we ended up taking extensions to get more security. That got us down to like 32-bit fields. Pretty cool. And then we were saying if we want even smaller fields, the problem is that we need to do FFTs and we need our traces to be long enough to be meaningful. And so the solution there was, or one of the solutions, I guess, is packing, right? This idea of trench code. And to fix packing, you have this sort of protocol here.
Exactly. That summarizes it well.
Amazing. Thank you very much, Jim.
Thank you, Nico.
And thanks for following with us.